Hello and welcome back. So we will continue our discussion of algorithms for data science, especially dealing with scale. Just a recap of what we have seen so far. So we saw what was a powerful lemma called the JL lemma so far in detail, and JL lemma is Johnson-Linden-Strauss lemma, and roughly it says the following, right? So if you have n points in some very high dimensional space, let's say RD, you can transform these points to n points in RK using the JL transform. And though in this course we saw one example of a JL transform, there are many other examples. The one that we saw was a scaled version of a Gaussian matrix, which does the job for us. So if you do that transform, then the pairwise distances are approximately preserved for every pair of data points in the original space that you started with, right? So and this happens, I think one of the important things was this happens with k. K is something like log n by epsilon squared, where n is the original number of data points and epsilon is the accuracy to which you want to preserve pairwise distances. So this is the JL lemma that we have already seen in detail. Now let's say we want to use this lemma for some machine learning or data science related application, and one of the most common applications that we will encounter in data science is the problem of nearest neighbors. So the nearest neighbor problem, I'm sure most of us are aware of this. Quick recap: so you have a bunch of n points, and then you are given a query point q, and you would want to know who is the nearest neighbor in the set of n points that you already have to the query point, right? So this is a very common problem that has several applications. The nearest neighbor classification algorithm itself is completely based on this, the k and n binary classification algorithm, where you pick the k nearest neighbors and then ask them for their votes based on their labels, and then you take the majority and you make a decision for the query point. Not just that, so that's one example where neighbors are important. But there are so many other applications in data science. For example, you might have an image and then you want to get the closest image in your data set to this image, or you might have a user who's walking into your platform, e-commerce platform, let's say, or a Netflix platform or something like that, and then you have some way to map the user to some very high dimensional space, and you want to find out the nearest movies in this user/movie space, commonly shared space, so that you can recommend those movies to that user, right? So finding the closest object is a very common theme in data science, and especially when you have a very high dimensional feature vector, it's going to take a lot of time to do this. Why does it take a lot of time? Because every time I have to measure distance in this very high dimension, and that takes a lot of time. So now one can ask, well, if I can reduce this dimensionality using JL lemma, then and apply the nearest neighbor, find the nearest neighbor in the reduced dimensional space, then do I gain anything? Of course we gain a lot, and let's just make this precise so that we'll see what we gain and what we perhaps don't gain, right? So let's call this it's the approximate nearest neighbor problem. Well, JL lemma, because we are going to use JL lemma, right? So which means that we are not going to directly get the nearest neighbor because distances are only preserved up to an approximation. But in a lot of applications, it's okay to have an approximate neighbor than the exact neighbor. For instance, in a movie recommendation problem, if you're going to gain in terms of speed, or the time taken to find the closest movie, it's okay if you don't find the closest movie, but then you are finding, let's say, an approximately the nearest neighbor, right? So you will be able to trade off quality, a little bit of quality of the neighbor, to the speed with which you are actually fetching the neighbor, right. So that's why we are okay to call this the approximate nearest neighbor problem. And if you want to apply JL lemma, yes, you can do that. So just to set some context, let's say you have x1 to xn, each xi is in d dimension, and then you map x1 to z1, xn to zn, each zi is in k dimension. So this is a pre-processing that happens even before we ask for nearest neighbors, right. So this is what is a pre-processing step. This is the JL transform step, let's say. So of course k is much smaller than d, log n by epsilon squared. So we are expecting k to be very small when compared to d. So how much pre-processing time does this take? Let's ask that question. Well, what has to happen? So we have to take a vector in d dimension and then map it to a vector in k dimension, and we have to do this n times. So how do we do this mapping? It's a linear mapping. So you take a k cross d matrix multiplied with the d dimensional vector. So which means that every there are k dot products that are being computed, and each dot product is a dot product between two d dimensional vectors, right. So and that's going to take order of d times, because dot product is just d multiplications and d additions. So it's order of d time, and then k of them have to be done to map one vector from high dimension to low dimension. And because there are n of such data points, each one takes k into d times. So the total time is something like order of n d k, right. So this is the amount of time that you need to do pre-processing, right. So this is like a one-time thing that we do, spending order of n d k time, map all the high dimensional guys to low dimensional guys, right. So that's done, right. So now you have several new users coming into the system. For every user you need to find out the nearest neighbor. So which means that you have dynamically multiple queries. So when you have a query, so let's say let's call this the query processing time. So once you get a query, so let's see what happens. So what's a query? A query is just a vector in d dimension. So the first thing one has to do is map this query point also to the low dimension. And how would you do that? So you would do it using again the JL transform. So that's going to let's say become ZQ, which is in RK, and this is going to take order of dk time, because there are again matrix of size kd that multiplies this vector of size d dimension. Now one thing to keep in mind generally is if you are going to answer so many queries in the test time, so to say, if you have a rough number that you are thinking about when you are answering these queries in the test time, now it's a good idea to choose this k in the pre-processing that includes the number of test points also, because when you are doing this query, you are mapping this high dimension guy to a low dimensional guy, and then you want pairwise distances to be preserved for the query guy also with respect to the original set of n people. So which means that if you had, let's say, 1000 data points to begin with, and then you are going to get 1000 more data points. So in effect, what you want is, if you can preserve all the 2000 points pairwise distances, then it means that implies that for every query point you are also going to preserve its pairwise distance to every point in the dataset, original dataset itself. Of course, it doesn't matter to preserve pairwise distances among the query points themselves, but because you don't know what the query points are a priori, might as well choose a k during the pre-processing time that allows for a certain number of query points also, which means that the dimensionality is going to go up from, let's say, log n over epsilon squared to log n plus m over epsilon squared, where m is this number of query points that you are expecting at test time, so that you are covering yourself for all the test data points as well, right. So that's a small point, but then if m is order of n, then you don't have to worry, right. So it's all covered in the constants, but I just wanted to let you know that. Okay, so let's talk about the query processing time. So this takes order of dk to go from d to k. That's not too much, I mean you have to do that, but so what happens after that is the problem, right. So in some sense, so now if you want to solve the nearest neighbor problem, now you need to look at zq and compute its distance to the other points in k dimension. The good thing is that they are in low dimension, right. So which means that you will have to compute the distance to these points, and so how would you compute the distance? Well, let's say it's a Euclidean distance for simplicity, which means this is going to be something like order of k, right. So there are two k dimensional vectors. I'm going to look at all the k components, subtract them, square them, I mean observe all that in the order. So it's going to be order of k for one distance computation, which is cheap because it's just order of k. But the question is, how many such distance computations we are allowed to do? Well, we will have to do n such distance computation, which means that the total time that I really have to take to find the nearest neighbor in k dimension is order of dk, well, to map from d to k plus nk to find n distances in the low dimension, right. So now as I find the distance, I can keep track of the minimum distance. So I don't spend anything extra to find the nearest neighbor, because once the n distances are computed, I mean I can also track the nearest neighbor, right. So that's not going to give me extra time, but this is the amount of time that is going to be incurred for one query point, right. Now this is okay. This is not too much if because we know k is something like log n. So this is something like d log n plus n log n. So basically, if I had to do this in the high dimension itself, let's say all the JL didn't happen. If I had to solve the nearest neighbor problem exactly, we don't even need approximations. Let's say if I had to solve the nearest neighbor problem exactly in high dimension, let's see how much time that would have taken. So the query point comes, there is no transformation or anything, there is no pre-processing, none of those things happen. So the query point comes, it's in d dimension, and then I will have to do it n different times. So that's going to take order of nd. Now order of nd might be much higher than order of nk plus kd, right. So this is nk plus kd essentially, right. So if k is small, so we are gaining, right. So we are definitely gaining because k is much smaller than n. Order of nk plus kd might be much smaller than order of nd, right. So which is a good thing. So we have gained in terms of time with respect to the standard nearest neighbor problem in the high dimension. So that's a good thing. The problem though in practice is, well, this works wonderfully well as long as n is reasonable, right. So this is good. When I say this, I mean this, right. It's order of nk plus dk is good if n is medium side, right. So when I say medium, well, depends. So it's a qualitative thing. So it depends on how many GPUs you have, how many CPUs you have, and things like that. But let's say roughly thousands or even tens of thousands, it's still okay, or even let's say a million is probably okay. But then if you go into the 10 to the 9 kind of a thing, right, so then for every query you will have to compute 10 to the 9 distances. So let's say you want to find the closest image, and then you have some kind of an image embedding that you have learned from a deep network or something like that. Now if you have 10 to the 9 images, and then for the new query image, well, you might have reduced the dimension of the image from a million to 1000. So you are doing quick calculation with respect to one image, but then there are too many images. When n is much larger than d and k, then this algorithm is going to suffer, right? So then though JL lemma gives the power to reduce dimensionality, our problem of nearest neighbor is not going to benefit, because it's not like we are throwing away points, right? So all the points are getting mapped to low dimension, so which means that all the points distances have to be calculated. So this is a problem for massively large data sets. Again, massive is a qualitative term. I mean, if I tell 10 to the 9 today, I mean, like 1 year later, there might be different advancement in technology where this might be medium. Then 10 to the 11 should be taken as massive, right? So whatever it is, that is not easy for us to compute with our resources. If the number of data points is more than that, then we are going to call that massive, right? So that's our definition of massive. So basically, in a different way, if we had to tell it in a different way, the question then we are asking is, can I somehow still do approximate nearest neighbor, but then not make it depend on order of n, right? So that's the kind of question that we want to ask, right? So